esteemed judges. Thank you. We're honored to be competing here next to the vast and bountiful Pacific Ocean, sheltered amongst the biodiversity of the temperate rainforest. My name is Clinton. These are my teammates, Faran, Tom, and Jimmy. And we are a team of electrical engineering students. And we believe that Canada's lands and oceans are worth protecting. And that's why we were so excited about this design problem. We care about this problem. And we think most people care. No one wants to see this. Our oceans are overrun with plastic and pollution and garbage. So our problem was to design a robot that could collect garbage from our oceans, and then we had to build a landlocked prototype equivalent that was from the robotics kit, the limited resources that we had provided. So this is what we came up with for our water design. We call it the Sea Scooper. So let's take a closer look. This is based off of and inspired by oil spill cleanup technology, wherein floating barriers encircle the surface contaminants, and also by Pacific Polynesian pontoon construction, where a low and wide dual hull system has withstood thousands of years and millions of miles of ocean travel. So it's well tested. So we got two hulls with their watertight sealed batteries and the electrical components, the processing and control unit in there. These are really cheap, just steel, aluminum, maybe even PVC tubes. The keels go beneath the water, providing a lot of anti-roll stability. And basically this thing has two scoopers on the front and just drives into the garbage. It's very simple, hardly any moving parts, except the claw. I'll get to that. And all the garbage flows into the pontoon behind it, collects here. If the robot ever needs to move backwards to dislodge anything that's in its throat, this pontoon gate can lower here so garbage doesn't flow back out and kind of undo all the work it's been doing. It has some solar panels for charging, and then that claw on the front actually can go down in between its legs and dislodge any sort of like logs or awkward objects that get caught in there. So we thought that would be really great. Eventually, maybe with machine learning or AI or image recognition, it could start to understand like chaos and dislodge and maybe try a few different actions. Because it's going to be way out in the ocean, you don't have to go out there and just dislodge every time something gets jammed. You need to have a way to clear its own jams. So what are our design considerations? We had many. We could choose to be either autonomous or manual. We had to bring these, for the landlocked design, we had to bring the correctly colored cans into the correct squares. And we also had to lift these bottles up and over into the lifesaver. So we also couldn't knock any of the cans out of the arena. That's part of the rules. You knock your can out, you can't retrieve it. And we had to do all of this with cost considerations in mind. It had to be as cheap and as robust, even mass manufacturable as possible. So with those considerations in mind, we had to come together with design. So you might think that we all got together, had a big discussion, brainstorming ideas back and forth, exchanging ideas about possible prototypes. But actually, no. Some research has shown that brainstorming as a group in an open discussion format can actually cut off the quietest voices, and they can actually smother really creative ideas before they're even allowed to grow from seed to forest.
Thanks, Ted. Hopefully this works. So first we learned what the design problem was. We sat down as a group, as the whole competition in the room. We saw what we were supposed to do. Then we went into that room, we saw what different components, what verticals can be used. And citing what Clint was saying, we decided to take kind of a unique approach. We didn't brainstorm back and forth with each other. We first sat down individually for 5 minutes apart, and we wrote down what we would do individually to solve this problem. And this way allowed us to come up with our own individual ideas that would come to fruition. And then after that, we then got together and then talked amongst ourselves about how to best solve this problem. So this is going to do this. Yeah. So first, I want to show you our drawings that we made individually, and I'll show you then after how it came together. So this is the first drawing. And this person was thinking about a gripper that can grab whatever and lift it up. I think they're thinking about the water balls and putting them in the lifesaver. You can see that they're thinking about a limit or a bump sensor as a tool tip so it can know to grab. And then there's some line sensors on the bottom. They're thinking about autonomous mode. You're going to see how in the next drawing, a kind of a different way of approaching this. They didn't think of the physical design, but they are actually drawing a state machine. You can see the numbers on the picture, and it correlates to the instructions on the bottom. There's actually a lot of instructions cut off, but that was more of a time domain approach of what they're going to do at what point. And then this person went a little old school and used pen and paper, and they actually had the best idea of us all, and they thought, let's create two static things on the side and let's bulldoze the can so we can get as many cans at once and then just push it into the squares. So after talking about that and coming together, we're not the best drawing, we're best drawers, we're engineering students. But this is kind of our end product, close to the end product. And you can see here, we have these are the stationary arms that push the cans. Here, you see the gripper, so two solutions. One works better for cans, the other works better for balls that need to have a little bit of lifting action. And before I go to the next point, some things that weren't on the slides, we needed to decide between the microcontrollers. We had the VEX Cortex, and we had the Lego EV3 kit. We had never used either of these. So we had to research as much for the competition, see how to program them, what the strengths and weaknesses of them were, and then kind of pray that our decision was correct, because you don't know what you don't know sometimes, right? And so you're going to run into issues. And so we went with the VEX. It just seemed like it had sturdier components, more components, and we have a programming base. So where the Lego was the block programming, so we're just more comfortable with that. The other design decision we had was we want to keep staying light. Steel, even though I'm an electrical engineer, I know that steel is 2.5 times as heavy as aluminum, and so that creates a little bit of torque in the frame, and that creates friction in the motor that we don't want. And since we don't know this kit, we had to use a kind of an example as a starting point. So we didn't want to reinvent the wheel too much. We needed to start with something and then build out from there. And yeah. And now I'm going to throw it up to Ron, who's going to talk about some of the deeper design decisions and how we implemented them.
Awesome, thank you, Jimmy. So now, when we were deciding on the run itself, we had two things to decide on. We need to choose either manual mode or autonomous mode. Now, there are advantages and disadvantages to both modes. So with manual mode, it's reliable and it can be counted on. But the problem is it's required for tests, and there's a human operating the machine, so it's prone to human error. And considering the spacing in the arena and the size of the object, we needed to minimize that as much as possible. Now, with manual mode, considering the way the world's headed today, and obviously the criteria, it's not as impressive. And for autonomous mode, it's ideal, but it requires several sensors, and we only had one line sensor available to us, so we couldn't feasibly incorporate our line sensor solution, which was basically an array of line sensors, and we would detect the gradient changes given the analog values and make the adjustments to the wheels to turn accordingly. Now, because of that, we narrowed our scope and figured we'd do manual first. Now, with pathing, there are a couple of problems we had to consider. since we're doing manual mode, we're really prone to user error. We're given a certain amount of parts, which means our size for the kit could not be below 30 centimeters. The parts itself had to be over that. So that created a problem in terms of maneuvering, which increased the human error possibilities. And we actually incorporate the thought process of the coefficient of friction because we didn't only want to navigate that terrain itself. We implemented a unique solution which actually traversed the outside terrain. So we had to calibrate the motors to drive straight, regardless of the terrain change. Now, so in terms of the solution, we had 3 goals in mind. We want to maximize the most efficient starting position for the robot itself. How we did this was we chose to be over here with the claw up the whole time applying constant torque, so it doesn't deviate with our first couple of pathing decisions. So our second goal was to clear up the arena, and our third goal was to obtain the most possible points. Now, how we did this was we started here with the claw up, navigated here, and basically pushed all of the red cans into the designated area. Did the same with the green cans. Now, we were at a position right here. Now, given this position, we needed to decide on the white water bottles or the yellow cans. Now, the white water bottles are worth more points, or worth 5 points, which means, and given the lack of symmetry in the yellow cans, it wasn't efficient to just grab the yellow cans and go in, given the size of the machine. So what we decided to do was grab the white bottles, and then finally, once the arena was clear of all the other objects, we could just go around, sweep the yellow cans, and put them in the designated area without, say, a turn going wrong and knocking over a block. And now I will pass it over to Tom, which will talk about some of the problems and solutions. Thanks.
Problems. This challenge presented our fair share of issues, and by troubleshooting and adapting, we were able to come up and implement some solutions to the following problems. So right off the bat, our microcontroller wasn't connecting to any of our computers, and also the manual control joystick wasn't pairing with it either. But by referencing some documents regarding the blinking lights, the blinking light codes on the controller, we were able to discover that there was a combination of the batteries not being charged enough, and the microcontroller was defaulting to this autonomous mode that didn't allow joystick connection. So by researching these documents, we found that we needed to add some code to make sure that it didn't enter this autonomous mode. Also, the line sensors that were crucial to our implementation of autonomous mode were in short supply. So we ended up having to switch gears, focus mainly on manual mode, and just optimize that manual mode, get it dialed in so that we can collect as many cans and as many bottles as quickly as possible. Also, we found that when we were testing, the cans were floating out of the push bin. We had a lot of cans there. So to combat this, we just added some extra side extensions on there just to keep all the cans in place. We found that the robot was doing great, and this was just due to unique differences between DCC motors, the properties like the friction or the resistances of the armatures of them. So when we were going full power, one motor would be going faster than another. So to combat this, we used a scaling factor to make sure that both of the motors would be going out at the same speed, and so we could control it accurately. The weight of the arm and the length of it, when it was loaded or unloaded, generated a moment large enough to make the robot tip forward. So to fix this, we just added a bunch of extra weight to the back there to make sure that it stays stationary and flat on the ground. When there was a bottle in the gripper, the arm wanted to drift down. So we need to, a solution to this was been to use a PID controller with an encoder to generate some feedback to keep it in the locked position. But we wanted to keep costs low. We didn't use the encoder, we just created a function that was that we used on the controller. Push a button, and we're able to lock the arm in any angle that we need. The end result is a robust, versatile, easy to use, and cost-effective robot. By acknowledging our team members' strengths and using effective troubleshooting, we were able to come up with a product that we are all proud to present to you here today. Thank you so much.